Okay, I'm sharing my screen now. Yeah. So hello all, welcome to the data structures class number 1. I'll keep my introduction for the end if time permits. For now, just my name should suffice. So I am Sukhil Kukreja. I'll be taking your class for data structures and algorithm. Uh, First, we'll look at introduction. So, what would introduction consist of? Is we'll just define the and what we are going to study in that, and then we'll also look at some of the necessary things that we will need when we study data structures. So, let's start with the definition. So, what is data structure? So, data structure can be defined as mathematical and logical model for organizing the interrelated data. Let's say it in a more intuitive way. Okay. Suppose you have a house, a new house that you are going to move into. Okay. What does your house consist of? It has a cupboard, suppose a shoe rack where you can keep your stuff. It has a big hall. Suppose you have brought your things with you. Okay. These are your things which you have brought when you are going to shift into your house. So what you'll do? You'll keep your clothes in the cupboard. You'll keep your sofa in the hall, and you'll keep your shoe in the shoe rack. Right. So what are you doing? This is nothing but your data. And where do you keep your data? In some sort of a storage, right? You have some storage already defined in your house and you keep that data there. So when we say data structures being mathematical, it basically means it's some sort of a predefined storage, right? Now, what does the logical mean here? So logical is, so you have your data organized in your house, okay? What do? You don't just keep it there, right? You take it out. You take out your clothes. You wear them. You show off your expensive shoes to your friends, right? So basically, what you are doing, you are taking your data, and then you are performing some sort of an operations on it, or you're doing some sort of a manipulation on it, right? So this is what the logical means. So logical means performing operations on the data. Hence the definition: mathematical and logical model of organizing the interrelated data of homogeneous or some same type of data, same type of data, right? So how are these data structures classified? So there are two broad categories of classification. One is your linear and other is non-linear. What does linear mean? Linear is when the elements are arranged in a sequential manner. Okay, so one thing to note here is a linear order is preserved in this type of data structure. Now, what does the linear order mean? Linear order basically means is that you should have when you are at a particular data point, you should have some info about the other one, like how to get to the next data. How could you achieve that? Could you think about it and let me, could you share some of your thoughts in that? How you could, maintain a linear order in a data? Any ideas? Come on, you can speak up. Okay, you're free to unmute yourself to ask any doubt or anything. Okay, first in, first out. Okay, yeah, that's a strategy. Yes, we could do that. So there could be like multiple ways to do that, right? So suppose how would be one of the ways. So you just store it sequentially. You store all the data sequentially. Suppose you have these are your memory locations. Okay, memory locations. So what do you do? So you just keep your data in the continuous memory locations, right? In this way, you know that to get to any data, you don't need to do anything extra. You already have this initial information that, okay, my data is stored in a continuous manner. What could be one of the other ways? It's that, suppose if you find yourself in a situation that your data is scattered, right? Suppose this is at 500, this is at 600, this is at 595. Your data is scattered. So how could you maintain a linear order in this type of situation? You could have, so with like each data point, you could have some information which would point you to the next part of the data, right? So when you are at this data, it will tell you, okay, I'm the first data element and the next one is a 600. So you get some sort of information, right? So this is one of the other ways in which you can preserve a linear order among the data, which are present in your data structure. So what are examples of some of your linear is that arrays, stacks, queues, linked lists. We'll be seeing each and every data structure. Today we'll do arrays. And similarly, what would be a nonlinear data structure? Where the linear order is not preserved, right? Elements are stored in nonlinear order. So I'll just give you an example. We won't go into much detail. Let's take an example of a hash table. So what happens in a hash table is that, suppose you have a table, okay, and you have different memory locations, 501, 502, and so on. So what happens in hashing is there's a hash function. Okay, let's treat this as a black box for now. Black box basically means some magic is happening inside this. We don't know it for now. Okay, this function is doing some magic and giving us an output. Suppose you have different keys, k1, k2. What you do, you give this key to the function, and it does some computation in its black box, and then it gives you an output and tells you, okay, store k1 at this location, store k2 at this location. Okay, we'll look into detail when we study hashing. So how, if you could see, the K1 is mapped at 501 and K2 is mapped at some, say, 510. So it's not stored in a linear way. So there's no way of knowing if K1 is at 501. I cannot say that K2 would be at 5. It could be anywhere, depending on what the hash function calculated its value. Right. So this is one of the ways in which the non-linearity comes into picture. So other non-linear data structures you could have is a trees, graph, hash table. We already looked into like an overview. So yeah, let me know if you have any doubts till here. Yeah. So yeah, kind of yes. So hash map will basically map your input, which is the same thing that we do in hash table. Hash sets, it's like a kind of an alias for the same thing to say. So yeah, we can use it interchangeably. Any more doubts on this? I hope the definition is clear and the classification broadly are clear. Okay, so we'll move on to the next slide. So now what we have looked at, we have defined like what are data structures. Now so the mathematical thing is sort of a little defined here. Now what about the logical part? So when we look into any type of data structure, we look at what kind of operations we can perform on that, right? So some of the very commonly used operations that we would see are, the first one is a traversing. Traversing says that we visit each and every element at least and at most once. So this is just a fancy way of writing. We visit every element exactly once. Okay, so there are many use cases in which traversing will be used, and we will look at them as we encounter each and every data structure. Second one is insertion. So insertion, as the definition suggests, is that adding an element into a data structure. Now here, suppose you have a data structure, okay? You have data structure and there are already some elements in it, okay? And suppose the capacity of this data structure is n. Now you have n number of elements in it. You have already filled this data structure. So what if I tell you, add one more to this? So naturally, as this capacity is already, it's already full. So what it would do? It would tell you error, right? So this type of error, we call it as overflow. Okay, when we cannot insert any more data into the data structure, that situation is called as overflow. Similarly, if we say for deletion, deletion is deleting an element from a data structure. Suppose you have another data structure, okay, and this is yeah. So this is empty at the moment. Okay, you had some data, you deleted it, and now it's empty. Now, what if I tell you delete one more element from this? So naturally, it would again result into error because there is nothing to delete. So this type of situation, we call it as underflow. Yeah. Next one is searching. Searching, as the name suggests, finding an element into a data structure. So in searching, what kind of output we can expect, right? So in searching, the type of output depends on the data structure used, on which data structure we are performing operation on. So for example, if I tell you, if we are looking into an array, and if we are searching for an element, and suppose we find it, if the search is successful, in that case, we return the index of the element. Okay, and if the search is unsuccessful, we return lower bound -1. So we'll look at this when we study arrays. I'm just giving you an example of what we return. Suppose you have a linked list or a tree. In that case, if your search is successful, you will return the address of the node, and in case it's unsuccessful, you just return null. Okay. The searching basically, the output of searching will depend on what kind of data structure you are using. The next operation is sorting and merging. So sorting, the definition says arranging elements of data structure in an increasing or a decreasing order. And similarly, merging says that combining, so combining two or more data structure of same type into one. So you have one data structure, you have another data structure, and you just combine it into you just combine both of them. So these operations we'll look into much more detail when we study algorithms. Okay, and for this subject, we'll mostly look at this 4 operations. Any doubts? I'll just it's overlapping. I'll remove this and draw it again. You can put your if you have any doubts, you can put it in the chat box till then. Let me just These will all be our basic operations which will look for every data structure. Okay. So any doubt, guys? Okay. Cool. Thank you. Let's move. So now before jumping into the data structure, we'll look at something called as complexity. Okay. So before complexity, let's see what is rate of growth. And even before rate of growth, I'll give you a situation. Okay. And I may need a volunteer for this. If anyone is brave enough, you can unmute yourself and just like feel free to interact with me. Suppose I send you to market. Okay, I send you to a market and I tell you buy a laptop and buy a Type C charging cable. Okay, so what would be the laptop cost you? It will be say 1 lakh rupees laptop and 121 rupees for your Type C cable. And when you come back, I tell you, tell me what was your total cost. So you would say, right? So you would approximately say, okay, yeah, it was around 1 lakh, right? You would approximate it to 1 lakh. Why would you do that? Because this is the cost of laptop far exceeds the cost of your cable, right? So you would apply some sort of approximation to it. So similarly, that's something but your rate of growth. So if I keep sending you to market and buy these type of things, you would generally ask me money. So if I tell you how much approximately money you will need, you will tell me, okay, give me this much, and you will approximate according to your most costliest item, right? So that's nothing but your rate of growth. So what does rate of growth say? The rate at which the running time increases as the function of input. Okay. So let's say I give you a function which is n to the power 4 plus 3n plus 5. Now tell me if I increase n. Okay. So if I keep on increasing n, which term in these three will grow the fastest? Just put it in the chat, unmute yourself, or and anything works fine. Right. Yeah, exactly. Very good. So when I look into this function and if I draw a graph, so the dominating term would be your n to the power 4, which is also called as your higher order term. And these terms are called as your lower order terms. So when we look at f of n, and we need to say, like, we need to give an idea to someone that how it grows, we would say, yeah, it approximately grows with n to power 4. This is nothing but your rate of growth. So the rate at which the running time increases as a function of input. Okay. So what are your commonly known rates of growth? So one would be your constant, logarithm would be log n, linear would be your n, log linear is n log n. Similarly, quadratic is n square, cubic n cube, and exponential is 2 to the power. Now, what does constant mean here? Can anyone say me what would be constant? So we understand that if I say n to the power 4, yeah, it's say n to the power 3, it's cubic. Okay. So sorry, let me erase this. Yeah, if I write a constant, what does that mean? Intuitively, what do you think? What happens? Yeah, Akash is typing something. Okay, single operation. Yeah, okay, single operation, correct. Or we could also, could we not say, so what do we define rate of growth as? The running time as a function of input, right? So basically, as the input will grow, we are telling how will the function or the algorithm or the process, how that will grow, right? So if we say that something is constant, we are just saying that it does not depend on input size. Oh, my bad. Just let me erase this. Yeah. It does not depend on your input size. Right. Yeah, it is the fastest. Yeah. Okay. Right. Agreed. But if we have to define it, we would say that with the increasing input size, our algorithm or our process, it does not change. Like it, whatever operations are needed to be done, it won't matter on the size of input. That's when we say a constant operation. If I give you an example, suppose I give you a list of items, okay, and I'm telling you that the items in this order are arranged according to their sizes. Okay, the smallest to biggest. And I tell you, find me the smallest element. What would you do? You would just go to the first element and you will tell me, okay, sir, this is your element. Right. Why? Because I have already told you that I am giving you an input which is already arranged in an increasing sort of manner. So even if I add like thousand or lakhs or crores of more objects to this, you know that the smallest will always be available at your first position. So hence, the number of steps or number of operations that you are needing to do is just a single operation, right? It could be a single or it could be a constant. Like suppose I tell you, I already gave you an input that the smallest element is at fifth position. Then like you have to travel till fifth position and you will find your element there. And irrespective of your input size, you will always find that element there. So that's how your constant comes into picture. Let me erase these. Okay, yeah. So are you getting how the constant? How do we see the rate of growth as? Okay, good. So now this is the rate of growth. So what is complexity then? Okay. So let's go to the next slide and let me write a little bit about complexity. So what does complexity say is that, so it tells us that how efficiently your, not your, in general, anyone's. So let me erase that. How efficiently, oh, sorry, I'll go back to that. Yeah. How efficient, I think, yeah. How efficiently an algorithm or, oh, okay, let me just write it a little below. I think, yeah. So it tells us how efficiently an algorithm or a process uses or utilizes resources. Okay. Now, what are these resources? Resources could be your time, your space. So, what is time complexity? Time complexity tells us that how running time increases, running time increases with input, with input, with increasing input size, right? And similarly, what space would tell us that how the memory usage increases with increasing input size, right? So how do we denote complexity then? So for denoting complexity, we already have defined our rate of growth, but we also need a notation, right? Now, why do we need a notation? I'll give you an example. Suppose I give you a random list of different sizes of objects, right? And I tell you, okay, find me the minimum. Okay, these are your n number of, I give you n elements. Now, can anyone tell me how many steps or comparisons or operations, how many steps or comparisons or operations would I need to find the minimum? Right? One thing we have to understand is we have to check for every element because this is a random list. Can someone type? Can someone? Okay, yeah, very good. Akash, n steps. Right. But now I tell you, okay, I have arranged it in a increasing manner. Now, how many steps do you take in this situation? Just come on, type it for me. The problem is still the same. You have to find the minimum. One, exactly. Very good. One step. So you see, right? Along with the input size, which is taken care by your ROG, what also matters is that how your input is arranged or defined, right? How your input is arranged. So because for different arrangement of input, you might have to do different type of work. So your complexity increases or decreases depending on your input. So for this, we need a notation and a rate of growth. So we'll just define. So we have something called as asymptotic notation. Why is it called asymptotic? I'll clear after we see the types of notation. So what we will look is that the three notations that we will look at is big O. Second one is your big omega. And third one is your theta notation. Okay. So this is denoted by a capital O. This is denoted by omega sign and theta with the theta sign. What does this give us? This gives us an upper bound. Similarly, omega, it gives us a lower bound. And theta, it gives us the average bound. Okay. Let us define it as a little more formally. Okay. I'll draw three graphs first. Mm. Suppose I have a function. This is your f of n. Here, f of n. And suppose I have another function, say p of n. Okay. So what does a big O notation? How do we, formally define it? So suppose you have some particular value of n equal to k. K here is greater than or equal to 0. So when we can say that after every value of n greater than k, greater than or equal to k, if we have an observation that f of n is less than or equal to some constant c multiplied by g of n, and here c is also greater than 0. So if we can say if a function, if there are two functions which satisfy this property, we say that f of n is O of g of n, right? So if I give you an example here, we looked at this function. Can we say that if that f of n is always less than or equal to, say, I'll take a big value, okay, 1000 into n to the power 4. Okay, if we substitute values in this, we can see that this can be satisfied, right? So in this case, we can say that f of n is O of n to the power 4, right? So everyone getting this? Give me an acknowledgement on the chat, please. Okay, good. So this is how you define your big O. Now, similarly, if you want to define our omega, how do we do that? Suppose this is your another g of n, okay, and you have another constant, same like for n equal to k, k greater than or equal to 0, if we can say that f of n is always greater than or equal to some constant c into g of n. So this is the condition in which we can say that f of n is sigma of g of n. Okay, so looking again at the same example, can I not say that f of n will always be greater than or equal to 0.5 into n to the power 4, right? Here the coefficient for n to the power 4 is 1. So this will always be greater than 0.5 into n to the power 4, right? So we can say that it is sigma of n to the power 4. Can we not say that? Okay, good. Yeah, thank you. So this is your omega and your big O. Big O, omega. Now what would be theta then? Okay. Now I'm giving you an hint. Okay, I'll just draw something, and I'm hoping you get a gist of it. What I'm going to write. Okay, you don't need to type it on anything. You just need to process it in your mind. Okay. So I'll just write it. So the f of n. So there exists the function called g of n, and there exists two constants c1 and c2, where c1 and c2 are both greater than 0, such that f of n is always less than or equal to c1 into g of n and c2 into, and is always greater than or equal to c2 into g of n. So can you not see that this is nothing but your omega, and this is nothing but your big O, and if you combine this, you get a theta. So what does theta say? So theta, you can say that theta exists when there exist omega and big O, and both are equal, right? So if we look at our example, we have O of n of n to the power 4 and omega of n to the power 4. So can we not also write theta of n to the power 4? Because both the upper as well as the lower bound exists. Hence, we can say that it is the average bound. The bound basically means it is bounding the function between some, a set of like a function with different constants. Everyone getting this? The theta, how does theta notation come out to be? We look at more examples, don't worry. But just if you get the gist of it, it's really great. Okay, thank you. Yeah, we'll look at some examples. So generally, what do we do is that, so these are your notations, and how do we use these notations? suppose you look at anything and like any algorithm or anything, and you want to analyze it. So you would use, oh, yeah. So you would use your big O notation. Okay, something here. When you would need to say for the worst case. Yeah. In the worst case, you will be using big O notation, and omega you will be using for the best case, and this you will be using theta for your average case. Now let's look at a fresh example. Okay. Okay. Does anyone have anything about why do we call it asymptotic? Do you have some curiosity to know why this is? Even like when I used to study, I didn't know that. But when you look into different resources, it's not a very big thing, but it's good to know, I think. So if you're curious, I can share. So before asymptotic, what's an asymptote? So asymptote is basically some line which appears to meet a function, but it never meets it. Okay, it just appears that it will meet, but it doesn't meet in a finite distance. So if you look at our like all our notations that we studied, doesn't it look like so? It always feels like the f of n will catch up to g of n, but it does never catch up to our function. So it provides a sort of an asymptotic bound to it. Like it appears to meet it, but it won't meet it. Okay, it will always still less than or equal to, or always greater than or equal to that function line. So yeah, I mean, yeah, could be interesting. I found it interesting when I read it for the first time. So yeah, so let's look at an example. Okay, I'll make some space here. Oh, it's overlapping. Yeah. Okay, so suppose, yeah, let's look at our previous example first, then we'll take a fresh example. So for this type of input, okay. Now, okay, sure. Yeah. Suppose the same thing, find minimum, right? Yeah. So so for this random input, can someone tell me, if I tell you the best case, what would be the number of steps in the best case for this input? Okay. For the upper one, this. Can you type in the chat? What would be the best case? Similarly, after that, you have to tell me what would be the worst case. No, no. See. My question is, what would be the minimum element? Okay, and you have a random input, right? So Akash, tell me one thing. I understand how you're thinking. So this is a random input, right? So you told me one. So how it could be one? Say you're saying me that I'll look at the first element, and if it's the minimum, I'll return that, right? But we don't know, right, if it's the minimum or not, because the input is random. So we have to like there's a compulsion to look at all the elements to confirm that we have a minimum element, right? We can't be sure on the first step because the input is random. So even in the best case, we require n number of steps. Yes, good. And what would be the worst case? Again, worst case will be n because we have to look at every element to find the minimum. So in this case, your best and worst are same. So we can say that the time complexity would be theta of n, right? And okay, so I'll give you one more example. Okay, so I give you a bag of keys. Okay, you have like the key means our door key. So all the keys are numbered, say 1, 2, 5, 7, 8. And I tell you, close your eyes, put your hand into the bag, and pick out a random key, and find me the one mm, which has like the minimum. And you already know that there are 5 keys present: 1, 2, 5, 7, 8. So in this case, what would be the best? Now tell me. Now, Akash, tell me. In this case, what would be the best thing? You close your eyes, you pull out a key. You already know that 1, 2, 5, 7, 8 are the key numbers present. Exactly, right. Arshi, very good. So best would be you just need one comparison, one step, one operation you need to do, right? And what would be the worst? Intuitively, if you see, yeah, n, very good. So the best is your constant and your worst is your n. So if we have to define a complexity of this program, we'll always go with the worst case because we don't care much about omega notation if both are different. So in that case, we'll say the complexity is O of n. So yeah, this is how your complexity comes into picture. So I like delved so much into it because this is something we encounter a lot when we study, say, data structures, say, algorithms, when we look into operations. So this skill needs to be, how to think about it, right? So this, I hope this helps you. So we'll also look at this notations into much more detail. Like we'll solve many more questions on this when we begin our algorithm. But for now, for understanding whatever we'll look into data structures, this should suffice. So please, feel free to put your doubts, or if you want to note anything, you can, unmute yourself and tell me. I can stop at that slide for a couple of a minute or so. If you need me to move front or back, you can put it in the chat as well. I'll hold at this slide for a minute. We will encounter this a lot. Right? Theta here. There are also another two notations, but uh, we won't look at that then now. And algorithms, yeah, definitely. So class, let me know when it's good to move, right? And if you need me to, go to a previous slide, please mention that as in the chat as well. Okay, class, is it all right if I move ahead? Or if you need me to go to the previous slide as well? Okay. Okay, good, good, good. Okay, I'm getting some acknowledgements. Thank you. Okay, so let's start with the hero of the class today. Okay, the star of the show. Array. So what is array? Array is nothing but collection of your homogeneous, similar elements. Okay, not much into the definition. We'll look into much more detail when we see its characteristics. So the characteristics are all the elements are stored in consecutive memory locations. So suppose this is your memory, your memory, and you have this location. Suppose this is these are your addresses, find with 1, with 2, 4, and so on. And what does the characteristic say? That all the elements are stored in a consecutive memory location. So suppose you have stored numbers here, 15, 18, 19, 20, 50. So these are your memory locations. So what does this say? We have to store it in a consecutive, so one after the other. So we are storing it. Okay, just good. So the next characteristic say that all the elements can be accessed using a set of indexes. Right. So if you look at here, these are your addresses. And how do we index that? So suppose the array starts from here. So index would be 0, 1, 2, 3, 4. These are your indexes. So the characteristic says that one, you have to have consecutive memory location, and two, you have to have some indexes, which you can uh, identify the array elements. How do we define an array? So the syntax for it goes like data type the array name and the size. If I give you an example here, it would be say integer of a comma 5. So this is your data type, this is your array name, and this is your size. So suppose it's a, the array a that we have defined here. Okay. Now, if you see here the starting index, starting index. So what is the starting index? Can someone tell me? So these are your set of your indices. So what is the starting index? 0. Good. And what is your last index? N minus 1. Yeah, right. Exactly. N minus 1. So, but in this case, it's 4, right? So your size is 5. 5 minus 1 is 4. Okay. So what we say is that what your starting index is also called as lower bound, and your last index is also called as your upper bound. Right. We will denote them as LB and UB. So this is how you define it in C. But what about in data structures when you are asked questions and stuff? How does the question come in the form? So it comes like an array name and with your indexes. So here, if for the last example, if I tell you, it would be a 0, 4. So this is your lower bound, and this is your upper bound. Now, some of the examples I could give you are, say you have a B array, it's 2, 5, and the set of indexes could be anything, say -2 to 2. Okay. Now, can you tell me something? If you want to know the size of array, and if I write upper bound minus lower bound, okay, I'm telling you this is the size of the array. So, would you agree or would you challenge me? I mean, I would like if you challenge me, but just apply it to this case. 4 minus 0 equal to 4. That doesn't seem right. Because we know the size is already 5. So, we are missing one thing. So, the formula for the size of arrays, upper bound minus lower bound, plus 1. Okay. Any doubts? Also, let me know if my handwriting is not readable. Okay. Um, I have not been known as the best handwriting person in my academics, so, but I'm trying my best. So, yeah. If it's clear, I can, go to the next slide. Yeah. Thank you. Okay. So, if I tell you, so you have an array, right? And if I tell you, okay, find me an address of the element at the index I. So I give you an index I, and I tell you, okay, give me what its address. Okay. So one thing, one thing we have to say is that when you are given an array, you will always have a base address, an address from which the array starts, right? So how would you define the location, the address of the ith element? So one thing is we would definitely need a base, because right, we need to know from where the array starts, plus w into relative index of I. What is okay, so first of all, let's get this out of the way. W is nothing but your per element size. Okay. And what would be your relative index be then? The relative index is number of elements before the element at element I, right? So if we have the base address, okay. Yeah. So we have the base address and it starts from here. Now we already have the per element size, and how many elements we need to go forward? We need to go this number of elements which are previous to the I, and then we can arrive at this location, which is nothing but your location of A of I. A of I. Yeah. So if we write it in a formula, how do we write it? It's base plus W. Now this is also your lower bound, right? And okay, so we don't need the upper bound. So can we not say that for getting the number of elements before this ith position, we can also write it as I minus lower bound, right? And if lower bound is 0, it will come out to be base plus w into I, right? Getting it? I'll have a question for you. If you say yes, I have a question for you then. Okay. Okay. So yeah. So couple of folks have said yes. So here you have a question then. So I've given you an array with the lower bound -5, with the upper bound of 5. I'm giving you the base address to be 1000, the per element size to be 2, and I'm asking you, give me the location of A of 0. Come on, right? And feel free to put your answers in the chat. I'm getting answers. Very good. And then I'll solve now concurrently. So I'll just write the formula first, which is your base plus w into I minus lower. This is your 1000 plus 2. Lower bound is -5. Very good, guys. So the answer comes out to be 1 pound. That's simple, right? So yeah, that's how you find an location of an element at an index I. Okay, yeah, I'll just give it like a minute or so to note this down. Also, can you tell me one thing? Meanwhile, others are noting, the ones who are done. Can you tell me what would be the complexity of this, of finding an element I? Sorry, the location of an element I? Can someone tell me? I'm just going to ask you every time, okay? What's the complexity? What's the complexity? Yeah, Akash is typing. Okay. Yeah, think about it now. Okay, I have an answer. Okay, Akash. So, yeah, someone is also typing. I'll let them type. Okay, good. See, first, like I have two things. Okay, so Akash and Arshi both. So be confident. Okay, just confident. Right, nothing is wrong. Nothing is right. In this class, there's no need to just type your whatever your gut tells you. Just type it one. Yeah, very good. So okay. So tell me one thing. Now, so I tell you to find an index of say first element or second or 1000 or 1 lakh or any element. If I tell you to find index, what are you essentially doing? You are performing one addition and you're performing one multiplication in finding that, right? So any size of array or any index, if I tell you find out, you will just perform these two operations, right? So with the growing input size, your complexity, like your number of steps or number of operations don't change. Hence, can we not say that it's just constant, hit of one, right? Think about it like that. How much work I am supposed to do this, and if I change my input, then how much additional work I'm doing, or if I'm doing any additional work, right? Yeah, very good. So yeah, so the complexity would be constant. Okay, good. And one more thing, so in the previous slide, just one small thing, the upper bound will always be greater than or equal to lower bound. Just a little note. So yeah, I hope this is clear, and we are good to move to next then. So this concludes our the mathematical part, the storage wala part of array. Now let's look at the logical. Yeah, it's something like a doctor would write. Okay, I'll erase this. Okay, let's move on to our operations. So as the tradition, we'll start with our traversing. So how would you traverse an array, right? So if I have an array, what kind of information do you have when you have an array? You have a lower bound and you have a upper bound. How would you traverse it? You would start from this and then you would increment it by one because it is a continuous memory location. You will check this, then you will move one step ahead, and you keep on till you reach the upper bound. So can we not write, if you want to write a pseudocode, can we not write for some variable k and we assign it to lower bound and it will go till upper bound? For that, we do some process of a of element at kth position, right? And in every iteration, we will increment this k by 1 till we reach the upper bound. So this is nothing but your traversing. But what are the use cases for traversing now? And there are many. So a couple of ones we'll look at. If I tell you, say, print all elements of the array. So in this case, what would your process become? Your process would simply become a print statement, right? It will just be a print a of k. Similarly, if I tell you another question, say, find me the sum of all elements. In this case, what you would have some, say, temporary result variable and you will assign it to 0. And then in each iteration, the process thing becomes res result equal to result plus your a of k. So this becomes your processing part of this problem. And at the end, you would just return the result. So these are just very simple use cases of traversing, and traversing is something very fundamental when it comes to data structure, because whatever you do on an array, like most of the things that you do on not just an array, on a data structure, you traverse it, you go through it. That's how like, without going through it, it's difficult to do some sort of operation on it, right? So this is like some of your use cases of traversing. Cool. Sound good? Then we can move to the next operation, which is your insertion. Guys, let me know if I need to stop on a slide, please. Okay, or to move ahead. I'll pause for some seconds here. Okay, I think we should be good to go ahead. Let's look at insertion. Okay, how to insert in an array. So suppose I tell you insert at an index. Right. We'll see three cases in this, right? Before starting, like before mentioning the case, let's just define some sort of an array. Suppose you have array like this, and already there are some elements stored into it, A, B, C, E, F, and so on. Yeah, these are your indexes 0, 1, 2, 3, 4, and right. These are your indexes. Now, the first case we see is case number 1, where this is your lower bound currently, and this is your upper bound. So if in this situation, the lower bound is 0, upper bound is 5, and your number of elements are 6. Okay. So if I tell you the index is upper bound plus 1. So basically, what does it mean? Insertion at the end. Right. So I say you, suppose insert I index and say you have to insert this element X. So can I say that I can, we have already have the array, we have all the index, we have the upper bound, and I already uh, have this thing that I have to insert the element at the upper bound plus one index. So can I not just do array of upper bound plus one equal to X? I put in the X, then I increment my upper bound because I have a new element, and then I also increase my number of elements because it has increased by size of one. So I just add my X here. So no, I won't do it here. I'll just create another here. So A, B, C, D, E, F, and I'll just insert the X here. Right. So for this case, what would be the complexity? Tell me. Yes. Yes, I see people typing. Exactly. Very good. So yeah, the complexity would be constant, say, bit of one. Because at the end, you just need to perform this same constant number of operations. Now, what would be your case 2? Case 2 would be, suppose your index is um, less than or equal to your upper bound or greater than your lower bound. So in this case, can you tell me if I am wanting to insert, okay, I'll change my pen color and show it in the original diagram itself. Change it to true. Yeah. So suppose I tell you, I need to insert it here. So what would you do? First, you will need to shift all these elements to one position, right? And then, and only then you can, when this position becomes empty, then you can, insert your element here. So can we not say that for this, we need to shift all elements from index plus one position to upper bound to one position right, and then insert, correct? So if this is your index that you need to insert from this I plus 1 to the upper bound, you need to move all the elements to one position, right? And then only you can insert the element to the to our index. So what would be your time complexity then in this case? Hmm? Yeah, correct. It can also be equal to your lower bound, right? Now for the insertion, let's look at the overall complexity. Okay. So if I tell you, um, what would be the minimum number of elements shifted? So in these two cases, what would be the minimum number of shifts that we need to make? And similarly, you have to tell me what would be the maximum number of elements we need to shift. Okay. So no. I'm not asking for complexity right now. What I'm asking is what is the minimum number of elements? Tell me the minimum number of elements that we need to shift. Suppose it's this case one. So in case one, how many elements did we shift? We shifted zero, right? No. So we did not shift any element, right? We just inserted it at the end. So we shifted zero elements. So yeah, I understand what maybe you are trying to say, the complexity. So yeah, the complexity will stay constant in case one. Yeah, yeah, right. And what were the maximum elements we need to shift when we insert it at a lower bound? So we need to shift all the elements, n. So in this case, we can say that our complexity is O of n because is best case and worst case don't match. Case 3, case 2, sorry. Yeah. So we can say that our insertion has an O of n time complexity. Time complexity of insertion in array. Yeah. Yeah, right. I see one. No, sorry, Akash just now. I'm not sure if the one was for, this complexity or something else. Or if you are getting this, how does this O of n come to be? the time complexity of insertion. Okay, good. So yeah, I'll just you know hold for a minute or so till you note this down. Okay, tell me one thing though. So I don't. So this is a new batch I'm thinking. So do you note everything, or you again go through the recordings or through the slides? What's the common process? Okay, yeah, good. Actually, that's better to do, no? No, yeah, good. So you need to tell me, okay, when to, we need to note, so stop for a minute or so. We are not in a hurry. Okay. Yeah, please. Also, we'll also be sharing the slides. After this, we'll look at, similarly we'll do for sort of a mirror image kind of thing or deletion as well. So, yeah. Once you get this intuition so like generally this happens like when you study DS or something. When you have like, get something for one particular thing, you automatically try to connect it with other operations or other things. Yeah. Okay. I think I can go ahead then. Yeah. Okay. Yeah. So, thank you. So similarly, we'll look at deletion. Let me go to my default red pen. Yeah. So again, we'll take a sample array. Oh, yeah. Sample array. Again, we'll have the same culprits. D, E, F, G. 0, 1, 2, 3, 4, 5, 6. Okay. So similarly, I'll take a case number 1. Now a deletion at index I. Right. Now the case 1 naturally would be index is equal to your upper bound. What would you do in that case? Okay. Okay, so here our number of elements are 7, lower bound is 0, and upper bound is 6. So in this case, when we have to delete the element from the last position, which is your upper bound, we would do nothing. We would just, decrement our upper bound and decrement our number of elements. Simple. What would be the complexity? Tell me. These all complexities I'm expecting from you, right? Because it's as kind of a mirror image of your insertion. So yeah, come on, type it up. Bingo. Good. Constant. Right. So, and what would be the other case? We could generally you can, this case 2 can also be split into case 3, but it doesn't create much of a difference. So, what would be the case 2? That your index is less than your upper bound and greater than or equal to your lower bound. Now think about it. I tell you to delete somewhere in the middle, right? Suppose I tell you to delete this element. This is your I. What you would do? Okay, for deleting it, you would simply, shift all the elements to the one position left, right? So can I not write that shift from index plus 1 to upper bound, shift all these elements to one position left, right? and then you decrement your upper bound, and then you decrement your number of elements, right? Now, if I ask you, similarly, if I ask you, complexity for this, what are the minimum number of elements shifted? Okay, give me the minimum first. How many elements did we shift in the minimum, like the first case? Number of elements shifted. Okay, yeah, exactly, 0. So this is your case 1. We shifted 0 element. Their complexity is constant. And what is the maximum number of elements shifted? This is your n minus 1. You agree? When we need to delete from the lower bound, right? In this case, we have to move all the elements to one position left. So case 3. So again, your complexities are different. So the time complexity for deletion will also be O of n. Time complexity of delete operation in array. Yes, please note it down. So this will look at the last operation, and then we'll look at some interesting questions. You guys understand my handwriting? Like, I just hope you. I mean, sometimes I would scribble, but mostly because it's self-understandable. Like this is shifted here. So, but I'll try to improve on my handwriting skills. So let's. I'll move ahead with the next operation there. So our last operation for would searching in an array. So there are two types of searches. So what could you? What could be one of the things? You have an array, and so you have an array, and one by one, you will go and search for an element, right? So this is how you can do it. This is one of the ways. Exactly. Very good. Linear. One is your linear search. What also? So Akash, you tell me, since you have mentioned linear, tell me also the complexity of linear search. We've already, sort of intuitively looked at it, but yeah, very good. Yeah, you're faster than me. Good. Yeah, often. And second would be a binary search. So in binary search, the only, there's a precondition, precondition, where it says that the array should be sorted, should be sorted. Exactly, good. And in this case, the complexity, anyone? Okay, it's actually log n, but it's log n. Hmm. So n log n is the sorting wala complexity. I think you are. Yeah. No. So array is already sorted. Okay, Akash, array is already sorted. We don't need to sort anything. The time complexity for binary search is what I was asking. Yeah, exactly. No worries. No worries. So, okay, let me ask you something. Does anyone know how this login? So we already like even in our colleges and we have looked at it a lot, right? Okay, binary search is login. But would you like to know how exactly the login comes, like mathematically how it comes out to be? Would you, because anyways, if you say no, I'm going to tell you. So, no, not now, but there's one more question that will solve. Then ultimately, I'll have to tell you then. So it's better, if I tell it now. So, okay, sure. So, what is binary search? Okay. So you are given this, say, a sorted array, 5, 6, 7, 8. Suppose you are given this array, and everyone, I hope everyone has this idea, but I'll just repeat that you start. So you have starting low, you have a high. What you do is you do a low plus high by 2. You find the mid element, you look at it, and you compare it with your target. And if the target is bigger, then you search in the right half of the array. And if the target is lower, you search in the left, because you already know that it's sorted. So you just need to look into the other half. So essentially what you are doing in this, you are reducing. Now, let me erase that and write again. Yeah. So basically in every step, you are reducing your problem size, your problem size by a factor of n by 2, right? You are 1 by 2, not n by 2. So at every step, you're halving. So I don't know what the English word for it, but you're making the problem size to be half, right? So suppose you have n elements, then you will, in the next step, you will have n by 2 and so on. So if you see, suppose we have this first step, okay? We have n, I have given you n element array. Then you compare it with the mid element, and in the second step, these are your steps. In the second step, you have an array of n by 2, then n by 4, or n by 2 square, you can say, and so on. So suppose at the kth step, you have an array size of n by 2 to the power k. Right? Everyone agreeing? So suppose you find your element at kth step. So when you find your element, that basically means that you just have a single element to search for. You cannot go left or right after this. You have the single element, you compare it with, and you find it. So can we not say that the sample size at the kth step, when you actually your search is successful or unsuccessful, you'll just have one element, right? So what does this say? N equal to 2 to the power k. And what does this say? K is your log n. So this is how your log n complexity comes out to be. So we are like, these are examples we will like look plenty of when we study algorithms, because there we encounter this a lot. This is just a simple one. So yeah. So I hope this is clear how, log n number of steps we need to find in binary search. So we'll see many, many more examples like this. Yeah. Okay. Good. Good. Thank you. Let's, yeah, so you just note it down. If you want, I can, erase it again and write it, because I think, okay, I'll just do it anyway. I'll quickly, because I like it when it's in a single file. Yeah. So that and two and so on. Okay. Size and for two, for two square. So yeah, I'll hold for a minute for you guys to know. So this concludes our operation part of it. Now we'll look at some interesting questions. So they will look at it like a concept, not a question. But there have been questions asked in GATE based on what we'll see next. So yeah. Say binary search conclude that k step in that case. Okay, I'll move ahead. I am assuming it's noted. Okay, thank you. Okay. I think I'll just remove this when I provide you guys slide. It's just the definition for the both searches. Yeah. Okay. So let's look at this thing. If I tell you, we need to find a minimum element in an array. So one ring with like one of the bell strings is okay. We need some traversing, right? And we are not going to need plenty of traversing whenever we look at it. So so for this particular question, I'll tell you both the methods, okay? But from the next problem onwards, I'll show you just the first, and you guys will try the other approach first, and then we'll discuss. So for finding minimum element, can I not write like suppose the minimum is at a of lower bound. I just assign it to the lower bound, and in the second step, I apply a for loop from lower bound plus one to upper bound, and in each step I'll increment it by one. And in every step of the for loop, what I'll check if the element at the kth position is less than your minimum, right? And if it is, then I'll just assign the minimum to a of k, right? So, and the third step, once the for loop concludes, I'll just return the minimum element. So what I'm essentially doing is I have my array. I assign minimum to this. Suppose it's 7. Then I go and I compare it with 8. Okay, this is not less than 7. Then I find 5. Then I, compare it with 7 and see, okay, 5 is less than 7. And this is my minimum. And so on. Right? I do it till the end of the array. And once the for loop concludes, I'll return. So the minimum will actually hold the minimum value. So what would be number of comparisons in this case? Because I'm comparing with each element from second position to the last, the number of comparisons will come out to be n minus 1. And complexity, come on, tell me the complexity. I need it with, okay, O of n. O of n, sorry, O of n is not wrong, O of n is correct. But can we not also say that in the best case or in the worst case, we need to anyways traverse the whole array? So would it not be better to write theta of n? O of n is correct. It's not wrong. It's correct. But it's just that the average case, if exists, we will say it's the average case. Okay. Theta of n. Good. So this is your like first method, the basic method to find a minimum element. Now next we'll look at another method. Let's see if that makes any, if it does any improvement to our existing this method. So note it down and then I'll move to the next method. Meanwhile, if you have any questions or anything, you can feel free to unmute or any even in any previous slides, you can put it in the chat. Anyways, thank you. I know, so this is the first slide. You might be a little hesitant to unmute yourself, but don't worry. You will become more informal as we go. So in both best case and worst case, number of comparisons will be unmentioned. Yeah, exactly. Because we need to find the minimum element, right? So we after at any stage we can't be sure if we have found the minimum. Will we complete like the complete traversing the array, right? It could be at the end. So in any case, we have to compare it with each element to find the minimum. Hence, the number of comparisons will always be n minus one in this case in finding the minimum element. Because yeah, okay, great, thank you. Okay, so should we move to the next then? Okay, I've already moved. So the next method is called as tournament method. Okay. So what do we so remember your World Cups or your so I'm not a big football watcher, but Premier League is it? Yeah, Premier League. So, but literally the Premier League doesn't work like World Cup. So consider knockout tournaments. Okay, what do knockout tournaments do? They pitch two teams against each other, and whichever wins moves forward, right? So similar is the concept with your tournament method. So what happens is, suppose I give you a list of elements, 15, 6, 8, 1, 2, 9, 10. See, so what you do, you will arrange matches between every, adjacent elements, and whichever wins moves to the next round. So in between 15 and 6, 6 is the lower element, so 6 wins. Here 1 will win, here will win 2, and here 3 will win. Similarly, in the next stage, here 1 wins, and here 2 wins. And so semi-final is 1, and in the final we have 1 and 2, and the ultimate winner is n. So what are we doing here exactly? We are doing comparison. We are comparing two elements at a time, right? And whichever loses, whichever wins, moves to the next. So what would be the number of comparisons? Can anyone tell me what are the number of comparisons in this? Yes, see, we are comparing two at a time. So that should give a hint somewhere. Sorry. So count it. If you're not sure, count it. So we have n elements, and how many comparisons have we done? 1, 2, 3, 4, 5, 6, and 7. So we have 8 elements, and we did 7 comparisons. Akash, would you like to think about it again? Just, see, take a small sample. Take 1, 2, 3, 4. Okay, n equal to 4. How many comparisons? 1, 2, we have 2 winners, and 3. 3 comparisons. So n equal to 4, we have 3 comparisons. N equal to 8, we have 7 comparisons. So the pattern tells us that number of comparisons would always be n minus 1. Do you agree, Akash? Yeah, I know how the n by 2 comes in mind. At first instinct, you always think, yeah, yeah. So n by so right, you are right, n by 2, but n by 2 is only for the first step, right? Hmm. So yeah, you will have n by 2, then n by 4, like that. You can derive it in the same way. How we derived for binary sub, it will give you the number of comparisons. So we are seeing that number of comparison is n minus 1. So naturally, we need to perform n minus 1 steps. So your complexity also comes out to be theta of n. So in average, you have to perform so in any case, you have to perform n minus 1 number of comparison. Okay. So this does not give any improvement, like literally no improvement we had with compared to our previous approach. Let's hope that this method, works for us for like the problems we are about to see. Note that down, and we'll go to the next. So basically, both are methods, the normal and the tournament method. Both have same result when we try to find the minimum element. We have no performance uh, benefit. I'll move to the next. So for the next question, for the next concept, I'll do the easy one, okay? And you guys try the second approach. Okay. So the question is finding. So now we have to find minimum as well as the maximum. Okay. So what my approach is. So if you're asking me, I'm solving it this way. Okay. First, what I'll do, I'll find the minimum element first. Do one pass. I'll do one traversing, and I'll find the minimum element. So the number of comparisons it will take me is n minus 1. And after I find the minimum, I'll do one more traversing and I'll find the max element. And it will again take me n minus 1 comparisons. So my answer is 2n minus 2. Okay, so this is my answer. Now what I need you guys to do is just try or think about it or try to solve it using our tournament method. Like try something, from that intuition, try if that gives an improvement. And if you're most invited, yeah? You're most welcome to unmute yourself if you have an approach or if you could. I'm not asking for the solution. I'm just asking for an idea. How would you go on about it? Okay. If you have any idea of any intuition that you can get, how we could, compare two elements at a time and find uh, minimum and maximum and hopefully get an improvement over my approach. Yeah, even you can type it in the chat, in short summary key. Okay, we could do it like this or like that. What I'll do in the meanwhile is I'll just, you know, write it slowly so that it also serves as a hint for you. Getting it something. I'm drawing hints, okay? So you need to decipher them, what I'm doing here. Okay, this is very straightforward. Let me remove this. Yeah. This is okay. This is good for a hint. One more thing I can do is that come on, do I have anyone with any? I just need a little anything. It might be right, it might be wrong. We don't care for now. Anyways, we are going to learn. But do you see anything, which could give you an idea with these colorful arrows that I'm that I'm drawing here? Type anything. What I might be doing here. Any idea, guys? Mhm. Should I? Okay, I will do one thing. Um, I'll start explaining if if it's all right, and we can do it a bit more interactively. So I'll ask you a few things, and you can tell me. Then you can type it. Then okay, we'll see how to approach this. So suppose I have this n elements. Okay. So what I'll do, this is similar to your tournament approach. So I'm comparing each consecutive elements, right? And I'll compare them. Okay. So A1, A2, I'll compare A3, A4, and so on. And whichever is the bigger element, suppose A1 is here, and whichever is the smaller, I put here. I make two boxes and I put it here. Okay. Similarly, I do it for all the pairs. 1, 2 to n minus 1, suppose. And you'll have, some elements are say A3 is here, A4 is here, you have AN here, AN9. So what we have done is we have completed our first step of tournament method, and then we have segregated our elements. So can we not say that after this there will be n minus 2 elements in the greater and in the n minus 2 elements in the smaller, right? So suppose whatever is the max element, the greatest element in this, and whatever is the smallest element, can we not say that the greatest element, no matter which number or which element it played a match with, it would have won because it is the greatest element in all of the input. So it is definitely present in our greater box, right? And whichever smallest element we have, so no matter which element it played a match with, it will definitely be in a smaller box, right? Do you guys agree with that? Okay, good. Yeah. So at the end of this first step, the number of elements in the smaller box would be n by 2 and in the greater box would be n by 2. Now what we need to do is that just, we need to find the max element from this box and minimum element from this box, right? So if you look at total number of comparisons which we will take, number of comparisons is first we have n by 2. Where this n by 2 come from? It comes from this first step, right? It comes from this first step. Now you guys tell me what the other two terms are. Okay. Yeah. Come on, tell me. So for finding maximum from this and for finding minimum from this. We have already looked at this. So, and remember, it gave us no improvement. So this contains n by 2 element and this contains n by 2 element, and we need to find max and min respectively. So how many comparisons? Yeah, bingo. Very good. N by 2 minus 1 and n by 2 minus 1. Very good. So what I'll do, I'll just remove it again and write it again. So it's a lot of space up. So if I have to write the total number of comparisons, it would be n by 2 for the first step, then n by 2 minus 1 for finding the maximum from first box, and n by 2 minus 1 for finding the minimum. So our total comes out to be 3n by 2 minus 2, which is nothing but 1.5n minus 2. So do you guys see an improvement in this? Yes, definitely we have an improvement. So yeah, our hope is not wasted. We hope that tournament method would help us, get a better result in future problems. So thankfully, yes. And what if, what if n is odd? Right. This is the case when n is even, right? You compare every two elements. So what if n is odd? Say we have a of n plus 1 here. What do you in this case? In this case, what we'll do is that we'll just copy the last element, because we just copy the last element to both boxes. Because we don't have any other element. All our elements are exhausted. So we'll copy it to both the boxes. If n is odd. In that case, what the number of comparisons will be? So the number of comparison in that case would be ceil of 3n by 2 minus 2. Okay, ceiling function basically means you will round it off to the higher integer. So if you have a 1.5, it rounds off to 2. Okay, one is ceil and one is floor. Floor function will round off your 1.5 to 1. Ceil, floor function. So now how does this ceil come out to be? Because we are we are copying our last element to both the boxes, it is bound to increase our number of comparison by 1. So if I give you an example to, understand it better, suppose I have 5 elements, 1, 2, 3, 4, 5. We compare 1 and 2, we compare 3 and 4. We have two boxes, right? So 1 comes here in the smaller box and 3 comes here, and 2 will come here, 4 will come here. Since 5 is the last element, we'll copy it to both the boxes. Now in this, to find the minimum, we need to do, so we have 3 elements, so we need to do two comparisons. And even here we need to do two comparisons. So what is the total number of comparisons? 1, 2, 2 plus 2 plus 2. Right, these two. So total number of comparisons come out to be 6. And what's your formula? 3n by 2 minus 1. So n is your 5. So 3 into 5 by 2, field function of this, minus 2, which is nothing but your 15 by 2. 15 by 2 is 7.5. So field function rounds off to the greater integer, right? So 7.5 rounds off to 2. Sorry, 8. And 8 minus 2 is your 6, which is your total number of comparisons here. So this is when we have n equal to odd. The slides are visible, right? I have written it at much bottom here. I hope it's visible. So just, example if n is odd. Yeah. So thankfully the tournament method gives us a good result. So yeah, you just note this down. This is something, there have been questions on this particular concept, on Git. We'll also look at them. So, yeah, I hope this is clear. Like when I studied this for the first time, it was like mind blowing for me. Like it may not be the same the case for you, but for me it was like, oh, how come this happened? So even like it's a little, once you know about this, you start thinking in that way. We'll do one more question like this. Then we'll see some gate questions and questions in general. So yeah, please, let me know when you have noted this down so that we can move to the next concept. So most of you must be in your, I think, third year or fourth year, right? In your, I mean, in your bachelor's. Should I move ahead if you are done with the movement of it? Okay, then thank you. So the next question is finding the second minimum element, right? So again, as the tradition goes, I'll tell you the first method, and then you guys can try, think about the how we could do it using the other method. So so it's me. So anyways do, I'll do one traversal and first find the minimum element, which will take me n minus one comparisons. Okay. And what I'll do, and the rest of the elements, for the rest of the elements, I'll traverse again and find minimum in that. Yeah, find minimum in rest of elements. So how many rest of elements I'll have? I'll have n minus rest of elements. So number of comparisons would be n minus 2. So in the rest of the elements, number of comparisons n minus 2. So total number of comparisons comes out to be 2n minus 3. So this is my approach. Okay. Now second approach, I'll just give some take a minute or so, think about how we could go. And I'll parallelly I'll start writing something which might give you a hint. So as soon as it clicks for you, you can just type it or say it aloud. Anyway, anything works. Okay, can anyone tell me this? Only element, the second minimum element will lose to. Okay, so which player it is that the second minimum element will lose to? Which is the only player that it can lose to? Can anyone tell me in the chat box? So look at the example. Okay, so this is our second minimum element, our answer basically. So in this whole list, what is the only element that can defeat this two? Exactly. Yeah. Very good. So one. What is one here? It's our absolute minimum, right? It's our absolute minimum element, the least element. Only this is the player that can defeat our second minimum element. So can we not say that in the after the tournament concludes, definitely like 100% guarantee that our answer, our second minimum element, would have played a match with with number one element, with the the least element, right? So if we see the opponent list of one, what are those elements? It's two, it's three, and it's five, right? So this is the opponent list of absolute minimum element, right? So are we not guarantee guaranteed to find a required answer, which is the second minimum in this list? Do you guys agree with this? It is a guarantee, right? If we analyze this list, it is a guarantee that we will find our second minimum element, right? Whatever is the least element in this list will be our answer, right? Can you Can that, can you guys see that? Exactly, yeah. So what in this step, what we need to do is that for every step, we need to maintain an opponent list for every element, right? So here, the whatever players have won, we have to keep their opponent list in record. So 5 played a match with 6, 7 played with 8. Now the one defeated 3, so his opponents become 2, comma 3, and 5 become 6, comma 8. So what this step is, okay, so we'll look at that later, but okay, let me mention it. It comes with a added space complexity, right? We need additional space to store all this, right? It may give us an improvement on time, but it is requiring a additional space. So just a, like a contextual thing for this. So now, what would be the size of this? Okay, remember our binary search thing and give me an idea about what could be the size of the opponent list once the tournament concludes, and what would be the approximate size of the this list. Remember how many? Very good, very good. Log n. Yeah. So log n would be a approximate size of this. So if I tell you, let me change my pen color to blue for this. Yeah. So if I tell you total number of comparisons, how many with total comparisons? Comparisons. Yeah. How many total comparisons? So n by 2 we did for the first step, right? For the first step of tournament method. And to find the minimum element from the size of list of log n, how many comparisons we need? If there was n, we needed n minus 1. If it's log n, we need, come on. Exactly, yeah. If there's log n, we need log n minus 1. Log n minus 1. So, okay, one thing. This is not n by 2, by the way. So total number of comparisons is n minus. That's okay. We are doing it for the whole. So first n by, yeah. So total number of comparisons for the first, for completing the tournament, we take n minus 1, and then we have log n minus 1. So what are our total number of comparisons? N plus log n minus 2. Okay. So 2n minus 3 and n plus log n minus 2. Is it an improvement? It is, right? Because log n is much smaller than your. So we can also write this as n plus n minus 3. So n is common. So log n is less than n, and this is a constant. So if we look for higher values, we take a lot less operations if we do it using a second method. So this also gives us an improvement for this question. Yeah. But the only thing is we need to maintain a list for every element that wins in every round. So it just adds a bit to our space complexity. So that is something to just have it in mind. It gives us an improvement in one aspect and costs us something in the other aspect. So yeah. After this, we have a couple of questions. We'll solve those and then we can conclude this part of this lecture. So please note it down. Could you explain the comparison part again? Yeah, sure. So, sure. So total number of comparisons, right? So look at this first step, right? We already looked at our this. So what is the first thing that we do is we arrange the tournament, right? We do the tournament thing and we conclude this tournament. And we already looked at this right here. In this, the tournament method takes n minus 1 comparison because we compare two elements at a time. So if there are, we took an example, if there were four elements, the total number of comparisons we take is three. For eight, we took seven. So we get to conclude the entire tournament, right? So similarly, we just do that in the first step here. Hence, the first part is n minus one. It comes from this part, and the log n minus one. It comes from looking for the absolute minimum in the the opponent list of the winner. This is your second. Its second comes from here, this part, and the first one from tournament method. Getting it, Akash? Okay, sure. Thank you. So what we did, we just, we looked at an example, like how to find a minimum. It did not give us an improvement, and we are just keeping on building on it. So yeah. Okay, so should we look at a question then? One is a straightforward question. Other question is like a very, according to me, it's a very nice question that came into it. So we'll look both questions. Please let me know when you are done noting the slide. Okay. Okay, sure. Thank you. So first question. An array of n number is given where n is an even number. So we don't need to worry about the field wala part, right? So the maximum as well as the minimum of this n number needs to be determined. Which of the following is true about the number of comparisons needed? So we have already solved this. So I would really like if you give me an answer for this. Exactly. Very nice. We have already solved this in detail. So this was like a pretty straightforward question. So yeah, and given that the even number, it helps to come at an answer because we don't need to care about the fill part of the thing. So yeah, so if everyone is clear, I would like to take the next question, like which is actually a very good question, and I'll give you some time to think about it, and then we can discuss that question. So we already solved this. Okay, so this is basically finding maximum and minimum. Yeah, so this is basically this question. 1.5 n minus 2. Okay, let's. Uh, I don't know if you're noting this because anyways you can have it from the slides later, and this is something we've already solved. So I would like to take the next question, which is a really good question. Just let me acknowledge in the chat if if it's all right if I move ahead. Okay, sure. Thank you. Okay, yeah. So think about this question, like read this and, I'll read it for you. So like P is an array containing n integers and let P be the lowest upper bound. Okay. This is a very, I really like this thing about people who set the gate questions is that, they'll, put this subtle hints in the questions without, explicitly stating it out. So it is P the lower upper bound on number of comparisons of array elements required to find the minimum and maximum values in an arbitrary array of n elements. What is correct? Think about it and we can discuss. If you have an answer, you can put it in the chat and we'll discuss it. I'll give you a couple of minutes to think about it. We have already solved this, but this requires like what we have seen. Remember what we have seen in the complexity when we were seeing complexity, and combine it with what we saw in this concept in max and min concept. So combine both things and think in that way. Okay. Do I have any ideas? Yes. I have mentioned a couple of hints on the slide here. Yeah, anything is fine. Like even if you give me half an answer, a quarter of an answer, a 10%, and anything is fine. Just how are we thinking about this? Can we at least, outright reject any option? Okay, don't tell me like, I'm not expecting the answer, but okay, tell me, um, all of you, tell me one option that we can outright reject. Okay, tell me that and we can start discussing then. Just tell me any option we can, reject at will, like just at looking at it, we'll reject it. Give me an option, A, B, C, D. One of these, give me option, we'll reject that and then we'll move on. Any option that you would like to, as you know that there's a lifeline called 50/50 in KBC. So I'm giving you 25/70 lifeline. You can erase one wrong answer. So yeah, give me one wrong answer and we'll start discussing. I need one wrong answer. Yeah, very good. I just need one wrong answer. Good. So this is not possible at all. So okay, we'll start discussing now. Good. Thank you. So it says that the p is greater than 2n minus 2, which is outright false because even our worst method gives us maximum these many comparisons. So it cannot be greater than that. So these so we can outright reject. Good. Thank you. Okay. So we'll discuss this. Okay. So why do I call it a subtle hint? Okay. If you look at the questions, no omega is mentioned. So no O is mentioned, no omega is mentioned, no theta is mentioned. Yet they are talking about bound, right? So they're not asking for like absolute number of comparisons, but they're asking us for the bound of it. Like how are the comparisons bounded? So from our study, we know that the worst method takes 2n minus 2, and the best we looked at takes 3, like CL of 3n by 2 minus 2 comparisons, right? So maximum uh, for the best method we have this, and for the worst method we have this. So lowest upper bound, what it basically means is that uh, worst comparison by best algorithm, right? So what is the best algorithm? It's 3n by 2 minus 2, our method to our tournament one, right? And if you remember what we looked in our complexity when we are learning complexity, so there's a graph and it is bounded by, it has a lower bound and an upper bound. So this is nothing but what these guys are asking, right? We need to find lower bound and we need to find the upper bound. So basically what we need is that we need a value of C1 and we need a value of C2, something like that. Okay. Now it may not be a theta thing. It's just a bound we are looking for. Okay. This could be better shown as two graphs rather than in one. So yeah. So we need two bounds for this. That's right. Fine. Yeah. So that's your upper bound and so that's your okay, lower bound. This is your lower bound. So upper bound and your lower bound. So we need two for the number of comparisons. So we know that 3n by 2 minus 2 is our number of, if we go to the best method, our number of comparisons will always be less than this, right? So if I take my constant C to be 1, can I not say that this into, let's say this is our G of n, right? And let's say T is our f of n. Can I not say that um, my 1 into 3n by 2 will always be less than or equal to, sorry, let me just, this will always be greater than or equal to 3n by 2 minus 2, right? So our T will always be less than or equal to 1 into 3n by 2. This is your constant C, and this gives us a upper bound, right? Now, where do I find this upper bound in all of these options? I see it here. I see this term here, and I see this here. but this gives me a lower bound. So we can outright reject this. So still there are like two computers to play from, right? So we have found the upper bound of this. Now how we go at looking at the lower bound? So take any algorithm, okay? Let's say we take this or we take this. Let's say we are taking this method too. Can I not say that if my constant is one into any abstract quantity x, it will be less than or equal to 1.5 into x, right? Why? Because if I apply the same principle to if I have constant 1 into n, I know that it will always be less than or equal to my uh, 3n by 2. So basically, this is my nothing but my p, my number of the bound on my comparison. So it will always be greater than n. Like my constant can be 1 here. So for the lower bound, I can say that they will always be greater than a constant n into here. Constant 1 into n. So this gives me my lower bound. So basically, the question what it becomes is that we just need to find bounds of this. We don't need absolute number of comparisons. So if you say if I have a single element, it will take 0 comparisons, but the formula gives me some other answer. So that's not the case. So they have explicitly mentioned that it's like not the absolute number of comparison, but we are looking at the bounds of it. So yeah, and the D option we can reject because it says that the number of comparisons is bounded by n, whereas we clearly know that even the best method it takes 3n by 2 minus. So we can reject this as well. So we have our answer. I like particularly found this question very like good. It doesn't give you outright. It doesn't even mention these notations to even think about in that direction. So you have to kind of you know um, merge the complexity concept as well as your maximum minimum concept. So it could be like a little tricky to get at this point, but if you think about it, how we look at bounds, then you're surely to get an idea of it. Is it at least like a 50% clarity is there for this question? I mean, even that's good. Okay, if there's a 50 to 60% clarity, it's fine at this moment because in the exam, even if you're not able to think about it, what good thing this question set us to is that if even if you are not able to think in this direction, you can do it via elimination method. You can eliminate option one, like we have this elimination method in competitive exams, right? So as you guys did for the first one, you rejected the A option, which was outright wrong. Similarly, you can go for the B option, right? So because this cannot be for the best algorithm, this p cannot be greater than 3n by 2. We know that. So this option is rejected. And the third option is p less than n. So the upper bound cannot be n because even the best algorithm takes 3n by 2. So we are only left with one option. See, is it getting any clear? Like, give me something in the chat if it's you will have to think about it a little bit. Like copy this slide and think about it. Like go on first do it the knockout way, then think about it from the complexity perspective. Hello, anyone? Yeah, any acknowledgement is fine. Even if you are not getting it at this point, it's not very straightforward thing to get. So even if you would like to discuss, you can unmute yourself. I know it's like way past the time. We can surely discuss it again because even our time today is almost done. So yeah, I'll you note this down and think about it. I'm not saying you'll 100% get it at this moment, but we can even discuss it again. So yeah, so if you guys could, so next we'll look into the next lecture. We'll stop here at this point for this lecture, and I'll just take a couple of minutes of your time. I'll just quickly introduce myself. Okay, relatively, we'll do it in next lecture. We are already way over time. So yeah, I hope all of this is clear. You may take your time to our notes, and yeah, we'll look on the next lecture, the concepts. Meanwhile, you guys are noting. If any other doubt is there, you can ask me. I'll try to upload these slides as soon as possible so that even you have, you have access to them in case you need them. Thank you all for attending. You are free to leave once you have noted it. Good night, everyone. Thank you. Thank you all. Thank you for coming. Okay, sure, sure. Sure, I'll go through it once again. Okay. Akash, so what we are looking for is the bound on this, right? So how do we look at it? So we know that our our best method, it gave us 3n by 2 minus 2 comparisons, right? And we want to bound on it. So if you remember yeah. So if you remember in the complexity, we were looking for this constants, right? So f of n is less than or equal to some constant into g of n. So similarly, same thing we are doing here. We just need to find a constant. We need to find constants. So if you look at 3n by 2, right? Can we not say that 3n by 2 will always be, you know, greater than, just a second, I need to erase it. Yeah. So 3n by 2 will always be greater than your 3n by 2 minus 2, right? We can say that, right? If x minus 2 is always less than or equal to x, right? We can say that. So this is what? This is nothing but your comparisons, what your best method takes. And we have found the upper bound on this, which is here. So the constant here becomes 1, and we found the upper bound on that. Similarly, for the lower bound, we can say that any number is less than 1.5 times of that number, right? So that's what we do here. So 1 into n, so x is replaced by n, and it is less than or equal to your 3n by 2 minus 2, which is your bound on your comparisons in this case. So that's how we found our lower bound. It's actually little tricky to get it because it kind of combines these two things. Uh, yeah, I know. It will like sit with it. We'll again discuss it in the next class. Not an issue. I'll try to give you another perspective of this. You sit with it for till next class, and this is the first thing I'll ask in the next class. Okay. Try to think about it, and meanwhile try to think about it that way, and we'll again discuss this. So yeah, thank you very much.